Bismillahirrahmanirrahim. Today we are going to start first session of our lecture number 4 of operating systems. Before to start our lecture number 4, we will take a quick overview of our lecture number 3. In lecture number 3, we discussed that this lecture will be based on our first course learning outcome: recognize operating system history, services, applications, and types. We start our discussion in lecture number 3 from timer, and we said a timer can be set to interrupt the computer after a specified period. So to interrupt the computer, we need timer. Okay, and we have two type of timer, that is fixed and variable timer. Okay, and then we said why we need timer, because we need timer to ensure that operating system maintain the control over CPU, and it's possible that sometime the user program are stuck like in infinite loop and they are not giving control back to the system. So that's why we need timer, and timer will interrupt the computer, and after that time when the interrupt will come, control will be automatically transferred to the operating system. Then we have seen that how we can implement the variable timer. That variable timer can be implemented by using two things: fixed rate clock and counter. So initially the operating system sets the counter, and then every time when the clock will tick, the counter will be decremented, and when the counter will reach 0, timer will interrupt the computer and control is then automatically transferred to the operating system. So what is timer, why we need timer, and how we can implement a variable timer. Now the next we have discussed the type of operating system, and we discuss 5 different type of operating system: multitasking operating system and single tasking operating system. And in multitasking and single tasking operating system, we said when a single program is allowed to run at a time, then the system is called single tasking operating system. But whenever we can run more than one program at a time or multiple tasks at a time, then it is called multitasking operating system. After this, we said that multitasking can be of two types: preemptive and cooperative. In preemptive, the operating system slice the CPU time and dedicate one slot to each of the program. But in cooperative multitasking, program currently in control of processor retain the control until it yield the control to another program voluntarily. So by force we are not able to take the control back. And in multi-user and single-user operating system, as its name shows, that multi-user operating system, it allow multiple users to access the system concurrently. This is the concurrently multiple user can access the system. So the time-sharing system are classified as a multi-user operating system, and also multi-user operating system are used on network of computers. So in multi-user operating system, which allows many different users to access same data and application program on the same network. It also used to communicate with each other, So in multi-user and single-user operating system, in single-user operating system, that only usable by a single user at a time. So like our home computer, our computer in office, in other work environment, so these are the single user operating system. So distributed operating system that manage a group of independent computers, and these the development of network computer that could be linked and communicate with each other. So they are linked with each other and they can communicate with each other. In distributed system, software and data may be distributed around the system and stored or programs and file may be stored on different storage devices which are located in different geographical location and may be accessed from the different computer terminals. So in distributed system, the important that data and software may be distributed around the system. It's not necessary that it is available only on one location, maybe in different locations. Then we discuss embedded systems, and embedded systems are designed to operate on small devices like our PDAs, smartphone, our tablets and so on. Because these type of embedded systems require limited number of resources and they are very compact and very efficient by design. So we have seen the examples that are Windows CE, FreeBSD and Minix 3 are some example of embedded systems. Then we have real-time operating system. It is a multitasking operating system that aims at executing real-time applications. Real-time operating systems use specialized scheduling algorithm and these real-time operating systems quickly respond to the event. And these are normally used to control complex system where we need a lot of processing. So like machine industrial system where we need high processing. So we use over there real-time operating systems. Then we start our discussion on process and we said the process is an instance of a computer program that is being executed. So a program, when the program is loaded into the memory, it becomes process. Whenever we are working in Windows or in any operating system, then in background many processes they are running at a time. So here we have discussed one example that we have only 3 programs running, but there may be 20 active processes. So how we can check? If we open the task manager, then we can see how many processes currently they are executing. Then we discuss the difference between active entity and passive entity. So we said that the file containing list of instructions stored on the disk often called executable file called passive entity, but process is an active entity. So we discuss the components of process. We have process stack, data section, heap and text section. So also we discuss the 5 different state of process: new, running, waiting, ready and terminated. So this was our lecture number 3. So today we are going to start the first session of our lecture number 4. So this lecture also belongs to course learning outcome 1. So because in last lecture we start our discussion on process and we have seen what is process, what are the component of process and what are the 5 state model in the process. So here the new thing, what is inter-process communication? What is this? That as its name shows, there is a communication between processes. When a process communicate with each other, it is called inter-process communication. So the communication is between the process. And why we need this communication? Maybe, for example, the output of first process need to pass to second one and so on to the other process. So maybe that one process is depending on the other process. So that's why maybe there is a communication between the 2 processes. So process control block. What is process control block? That a process is represented in the operating system by process control block. So it is another name that we can use, the task control block. So how we will represent process in a memory? So we use process control block to represent the process in memory. So also the process control block consists of process state, process number, program counter, register, memory limits, list of open files, and so on. So these are some of the component of process control block. So here what is process control block? That each process is represented in operating system by process control block. So we use process control block to represent the process in the memory. So we will discuss all these components: process state, process number, program counter, register limits, memory limits, and list of open file in coming slides. So we start from process state. So process state. So as already we discussed in second session of our lecture number 3, that we have mainly 5 states: new, ready, running, waiting, and terminate. So new, as already we discussed in detail what is meaning of new state, ready, running, and waiting state. Program counter. The second component is program counter. So program counter indicates the address of next instruction to be executed for the process. This is same as we discussed in lecture number 3, that over there process have some program counter. So program counter, which instruction we have to execute, this has the information about that instruction, because the CPU don't know. He is just following the instructions. Which instruction our processor will get, he will work accordingly. So program counter contains the address of the next instruction to be executed. So first he will give one instruction, and then after that he will, when the CPU will finish the execution, he will give the second instruction, and so on. So this is second component of process control block, that program counter. Next, that's very important, that CPU registers. This also component of process control block, CPU register. These registers vary in the number and type, and it depends on the computer architecture. The architecture, on the base of architecture we can say that how many CPU register it has and what are the type of the register. But commonly the 4 register that will be available in all type of the architectures. So first one, the important one, accumulators. So what is the purpose of accumulator? This register is register in which the intermediate arithmetic and logic results are stored. To store the arithmetic and logical results, we use accumulators. So if I give you one example, that I have 3 variables A, B, and C, and all these 3 variable type is integer, let's suppose, and I want to get the result of A plus B plus C. So first operation that we will perform, it will be suppose A plus B. So result of A plus B will be stored somewhere, and then this result will be added with the C, then we will get the complete result of A, B, and C. Okay, so an intermediate arithmetic and logical results we need to store, and we need some register to store this. So what register we will use then? That is called accumulators. Then next type of registers are index registers. The index registers are used to modifying the operand address during the runtime of a program. Now, in any expression we have 2 very important things: operand and operators. Now, if I have declared 2 variables, integer A and integer B, now these 2 variables will get some memory in space, and there will be some address of these variables in memory. Now during runtime, which register will be responsible to modify the operand address? This will be index register. So this is responsibility of index register. If address is changed, modify mean to change some location, address location is changed. So who will be the responsible? Who will handle this? These are the index registers. Then we have stack pointers. So stack is that used to give the address of stack area. If you remember, we have discussed in lecture number 3 that stack, it contains three things, that is local variables, function parameters, and return address. This is the thing that are included in the stack when we discuss in process in lecture number 3. So here in process control block, stack pointer is used to give the address of the stack area. What is the address of the stack? Where the local variable and parameters to subroutines are stored. What is the area? What is the address of that stack area? So who will be the responsible? That is stack pointer. Then we have general purpose registers. And in general purpose register is a small amount of storage available on the CPU. Now this is what? This general purpose register is a type of memory. Okay, this is a storage that is available on CPU and whose contents can be accessed more quickly than storage available elsewhere, because that is very close to the CPU, that is available on the CPU. So the what is in this can be easily accessed. So these are the four main registers that process control block has. So what are these registers? That is first one, accumulator, and which is used to store the intermediate arithmetic and logic results. Then we have index registers, and this register is used for modifying operand address when the program is in running mode. Then we have stack pointer, and which is used to give the address of stack area. Then we have general purpose register, and what is general purpose register? It is actually a small amount of storage which is available on CPU. So whatever we will store in this storage can be easily accessible by the CPU. Okay. Next we have CPU scheduling information, that is also component of our process control block. So what information it include? It include process priority, pointer to scheduling queue, and any other scheduling parameter. So everything that is related to scheduling. So this will be responsibility of CPU scheduling information to store in process control block. Then we have another component of process control block, that is memory management information. So these scheduling and memory management information we will discuss in detail. These are the separate topics that we have to discuss. But here memory management information is what? That it includes the value of base and limit register, page table, or the segment table. So page table, segmentation, and everything that we will discuss in our coming lectures. But this information will be also in process control block. Okay, CPU scheduling information and memory management information. After that, we have another component of process control block which is called accounting information. So this information includes the amount of CPU and real time used, time limits, account number, job or process number, and so on. That because we have discussed in our lecture number 3 that each process have a process ID. So process number or job number. Okay. So of course whenever we have a process, he need time to execute. So amount of CPU or real time used, which time he used, the CPU. Okay, and what was the actual time he stay in memory, in waiting state, in ready state, or in running state. So this is total time. So what are the time limits? This informations we need to store, account numbers. Okay, so all these information that are related to accounting information, so we will store, and these are called accounting information. Then the last one, we have IO status information. So IO, input and output devices. So this is, it includes the list of IO devices allocated to process. So how many devices are allocated to a process? If we have, suppose 3 processes currently, okay, in our system, P1, P2 and P3. So which devices are allocated to P1, which devices are allocated to P2 and P3, and so on, and list all the list of open files, which are the files which are open, and so on. Many information that everything related to IO, input output, that we need to store. What is the status of IO devices? Currently it is free, it is allocated, and if it is allocated, it is allocated to whom? To which process? Okay, so we need to store all this information in our system. Next slide shows the diagram which shows the CPU switch from process to process. This is just a simple example that if we have more than one process, and we said in previous slides that time sharing, that is, process is moving from one CPU is moving from one process to another process so frequently. So how it is moving? Let's suppose if here, if you see that we have process P0, this is your process P0, and this is process P1, and in between the P0 and P1 you are able to see here operating system. So we have also operating system. Now here if you see the double line shows currently in execution mode, and single line shows that it is idle, mean not currently in running, it's idle. Okay, now this diagram shows that P0 start execution and executing, and after some time this process we need to stop. Now it depends that it's maybe time slice is expired, so we need to stop this. When we will stop, then there will be some interrupt came and it stop and given the control back to the operating system. If you see this arrow, it is going and giving control back to operating system. But when we will give control back to operating system, it is very important that to store the state of this process P0. So we will store the state of process P0 into process control block. So here it is written, if you see PCB 0, it means the state we have saved in the process control block 0. This 0 is just to differentiate between different processes, because for each process we have his own process control block. Okay, so this process control block is used to represent the process in the operating system. So we will save the state into process control block because later we need this state. Okay, now this dot, it is showing that control is with operating system, and after some time again he given control back to the process P1. So reload state from PCB1. So it means maybe before P0 start execution, P1 was already executed some portion of his instructions. So what is the state that was stored for process P1? We need to reload, and then if you see the control is going to the P1, process P1. Now P1 is in execution mode. Okay, P1 is in execution mode. Maybe after some time when the time slice expire or some interrupt came or any system call, then what we have to do, we need to save the state of process P1 in process control block. So here if you see PCB1 mean that process control block 1, that we need to save the state, and then again the control is with operating system, and after some time now operating system is going to give control back to process P0, and then what he has to do, reload state from process control block 0. So here if you see this diagram, and whenever we are going to stop any process, we need to save the state into his process control block, and whenever we are going to execute the process, we need to reload the state from process control block. Okay, so here this diagram is very simple. It's showing how the CPU is switching from one process to another process. Now if there is a question that we have three processes, so if you understand this switching from one process to another process, easily you can make for three processes, for four processes, and so on. It's very easy. Simply the thing that you need to understand, whenever we are going to stop the process, we need to save his state. What is his current state? It's waiting state, ready state. So what is currently? And then when you are going to execute any process, you need to reload the state from process control block. Okay. So this was CPU switch from process to process. Now next is time sharing. So what is time sharing? Its name shows that objective of time sharing is to switch the CPU among processes. So frequently that the user can interact with each process while it is running. Because as we already have discussed that in our system, not only one process is executing, we have many processes. At a time they are in execution mode. So these processes, we have one CPU to execute all these processes. So our CPU is switching from one process to another process, and this switching is very fast. Okay, so this is called time sharing. We are sharing the time of CPU. Okay, there is this one schedule, and it depends. On next lecture we will discuss some scheduling algorithm. So we have different scheduling algorithm that we are using to do this, that we are switching the CPU among different processes, because at a time maybe 50 processes are running, but actually we are working with 1-2 processes, but on the back end 50 processes are running. So at that time actually the concept of time sharing comes, that CPU is moving from one process to another process, and this movement, it's too fast, and that we are not able to imagine that our process is stopped, but it is moving from one, because we don't want to keep our CPU idle. So whenever there is a small time, something waiting, CPU switch to another process. So this is called concept of time sharing. So next, process scheduler and process identifier. That already you know that what is scheduler and what is identifier. Process scheduler, the purpose of process scheduler is to select an available process, possibly from set of several processes, for the program executing on the CPU. Okay, so this is job of the process scheduler. If you remember, and if you go to the lecture number 3, last slide, that here we have this diagram, process state diagram, and here from ready state, if you see that there is a scheduler dispatch, that from ready state process move to running state. So who will be responsible to move from process from ready state to running state? Because it's possible that we have many processes in a queue in ready state. So process scheduler will be responsible to move process from ready state to running state. Now, what schedule it will use, we will discuss. We have many scheduling algorithm: first come first serve, shortest job first, round robin, and priority queue. So many we have. So in coming lectures we will discuss these algorithm. But here the software scheduler, this is responsibility of scheduler to move process from ready to running state. Okay, so this is also in process it's very important that we must have process to for smooth execution of all the process. The purpose of process scheduler is to select an available process, okay, because maybe available process are more than one, so we need to select one for executing on the CPU. Next, we have process identifier, that is uniquely identify a process. Process identifier PID normally we will use, that is to identify a process, okay, and this number must be unique. So this process identifier we will see in lab, how we can see the process identifier, how we can create process. Okay, so there are some concepts related to lab, so we will discuss in more detail in lab during lab session. So we will stop our discussion for session 1 of our lecture number 4. So we will just go and we will take a quick overview what we have discussed today. We start our discussion from inter-process communication. As its name shows, as I discussed, that inter-process communication means that two processes or more than two processes, they are communicating with each other. Okay, so this communication is between process, nothing else. Only process they are communicating with each other. Okay, so why they are communicating? I mentioned here one example. Maybe the output of first process need to pass to second one, and that second process is depending on the process one. When the process one will finish his work, it will generate some output, and that output will be the input for process one. So that's why first process is communicating with the second process. So this is one reason. We have many reasons that the process they are communicating with each other. Then the important thing that we discuss, that is process control block. What is process control block? That we discuss the process is represented in operating system by process control block. How we will represent a process in operating system? That we will use process control block, and this is also called task control block. Okay, so we have some components of process control block, that is process state, program, counter. So states, we have 5 states. The process will be in one of these states, maybe in new state, in ready, in running, in waiting, and so on. Then we have program counter. That program counter indicate the address of next instruction to be executed. So program counter will tell the CPU which instruction you have to execute, and after finishing this instruction which you have to execute next, and so on. So this will be the responsibility of program counter. Then the important thing that we discuss, CPU registers, and we said that these registers depend on the architecture, how many registers and what are the type of the registers. So we have mainly the registers, we have accumulator, index registers, we have stack pointers, we have general purpose register. So what accumulator are doing, they are used to store the intermediate arithmetic and logic results. And what is the purpose of index registers? These index registers are used to modifying operand address during program runtime. Whenever we are running the program, so these registers are used to modify the operand address. Stack pointer, it gives the address of the stack area, and we know that the stack area, what information we have local variables, we have function parameters, and we have mainly return address. Then we have general purpose register, and this is a small amount of storage, and that is on CPU. So what is stored in this storage can be easily accessed by the CPU if we compare with any other storage devices. So these are the main CPU registers: accumulator, index registers, stack pointers, and general purpose registers. Then we have discussed CPU scheduling information and memory management information, and we said that these two topics will be discussed in detail in coming lectures. So briefly here, what is CPU scheduling information? It includes process priority pointed to scheduling queue and any other scheduling parameters. Anything that is related to scheduling, it will be included in CPU scheduling information. Then we have memory management information, which include the value of base and limit register, page table, and segment tables. Next, we have discussed accounting information and IO status information. In accounting information, everything related to accounting mean amount of CPU in real time, how much time a process take, time limits, what was the time limits, job number, process number or account number, and so everything that are related to accounting, it will be stored here. Then IO status information, it include the list of IO devices which are allocated to a process, a list of open file, and so on. Okay. So this everything related to input output devices we have to store. Then we have seen one diagram which is showing the switch of CPU from process to process. There is two processes, P0 and P1. The important thing is, whenever we are going to execute any process, we need to reload the state from process control block, from his process control block, and whenever we are going to stop any process, we need to save his current state into process control block. So here process, sometime it is executing, sometime idle, and when the interrupt comes and or any system call, we need to stop the process and we need to reload the process. So there is a way how we have to stop the process and how we can reload the process. Then we have seen the time sharing. What is objective of time sharing? To switch the CPU among process so frequently. So switching process is all the time CPU is switching between different processes. Then we have process scheduler and process identifier. Scheduler, because we have many processes available, to select one process and give to the CPU for executing. And process identifier, that is number which is uniquely identify any process. Okay. Now this was our first session of lecture number 4. So if you have any question, you can send me email on my email address, or you can visit my office during office hours.